Thank you, Ian. So, as Ian mentioned, my name is Romain Figuière. I'm a PhD student at Stockholm University, and today I'm going to talk about a project I did in cooperation with Björn van Dijk from Stockholm University and the University of Amsterdam, where we tested the implementation of the essential use concept and the functional substitution concept to manage PMT substances in cosmetic products. So the essential use concept, for those of you that wouldn't know, it has been first introduced the Montreal Protocol as a tool to phase out ozone-depleting substances, when it has been agreed that those substances should be banned, except for those uses that would be necessary for the health, safety, and critical for the functioning of society, and for which there are no alternative available. So for those uses that would be essential. The functional substitution concept has been defined by a group of researchers in 2015 when they suggested that the alternative assessment should be focused on the function that is provided by the chemical of concern by simultaneously considering the chemical function, the end-use function in the final product, and the function of the service. So in other words, whether the service provided by the chemical to society. And last year, Roy and colleagues suggested to combine both the essential use concept and the functional substitution approach in an alternative assessment, so it should be able to accelerate the alternative assessment and be able to identify safer alternatives. So that's what we based our project on. And the objective was to test this approach on a concrete case study, and we chose cosmetic products because it has been shown that cosmetics are the source of PMT substances in the environment, and also it was really easy as a candidate to get to access the data of what type of substances are used in cosmetics and for what reasons. So we use this framework as a base for developing our method. So there are three main steps. The first one is to scope the assessment. In other words, identifying the chemical of concern and its technical function. Then the assessment itself, where we have to answer three main questions. First one is the function really needed for the performance of the product? Then is the use of the chemical of concern necessary for health, safety, and functioning of society? And are there no available alternatives that would be safer for human health and the environment? And if the answer to these three questions is yes, then the use can be considered as essential. If the answer to one of those questions is no, then the use is non-essential and the substance can just be phased out of from the products. So to identify the chemical of concern, we use the COSING database as a starting point. So there are like 10,000 substances that are listed in there, so it's 10,000 substances that can be used in cosmetic products. We screen these substances and we identify the PMT and vPvM based on the results that Hans Peter already mentioned a bit earlier. We found out that 50 of those substances can be PMT or vPvM. And then we use two databases provided by Chemie Lupin and Cosmetics that list the ingredients of the cosmetic products that are available on the market. And we found out that around 6% of cosmetic products actually contain PMT substances. Based on this, and based on the occurrence of the substances in cosmetic products, we selected three different case studies to define the technical function of these PMTs. The first one was thimbazole, which is an anti-dandruff agent that is used in shampoos. Second one was benzophenone 4, which is a UV filter and UV absorber used in all types of cosmetic products. And the third one was Allura Red, which is a red pigment used also in all types of cosmetic products. So once we have defined the technical function, we ask ourselves, is this technical function necessary for the performance of the cosmetic products? For thimbazole, it was pretty straightforward. It's an anti-dandruff agent used in shampoo for which you want to have anti-dandruff properties. So then, yes, it is necessary for the technical performance of the product. For benzophenone 4, so as I said, it's used as UV filter. So UV filter are the chemicals that are used in the sun cream to protect the skin from sunlight. So here again, it's necessary for the technical performance of the sun cream. It's also used as UV absorber. UV absorber, based on the interview that we had with industries, UV absorbers are used to protect the formulation of the cosmetic products from degradation by the sunlight. So it's used in cream. They said that if the cream doesn't have these type of chemicals, it will turn into mayonnaise after a few days. So it's used in cream and also in the makeup, such as or like lipstick, nail polish, so then the color stay on the skin longer for a longer time. So again, for this, it improves the duration of the use. So we considered that it was also necessary for the technical performance of the product. For Aloe red, it's used first in like makeup, again lipstick, etc., to provide a red color to a type of surface. So, for instance, if you want to buy a red lipstick, you expect your lips to be red afterwards. So then we consider that for this application, it was necessary for the technical performance of the product. But it's also used to provide a color to the formulation itself. For example, it's used in soap, like a strawberry soap, like a soap that's not like strawberries, so it's red because then, as a consumer, we expect the soap to be red. Maybe, I don't know. But for these, the industry actually said that they are changing the formulation and they're actually just changing the packaging, so the packaging is becoming red, but the formulation is not red. So for this, we think that it is not necessary for the technical performance, it's just a marketing purpose. So in those cases, the substance can just be taken out of the formulation. So once we answered this question, we turn to the assessment of alternative. We based our work on the framework that is published by ECHA in the guidance for brand reputation for authorization. The assessment of alternative, there are like three main steps. First, identifying the alternative, then assessing the alternative based on their technical feasibility, economical feasibility, and their hazard profile. And then based on all these, compare the alternatives to select the better one. So to identify the alternative, we use the causing database again as basis. Then we also use a special claim and a list of authorized food additives to identify the potential alternative. Then we shortlist the potential candidates. So it means that after screening all these databases, we ended up with like 50 alternatives per case study, which was way too much. So then we took substance out based on things that we already know. So we used the subsport database, which is a collection of around 30 lists of chemicals that are restricted either by the industry, the NGOs, or by the authorities. We also screen out substances that are in the Annex 3 of the Cosmetic Product Regulation, which is substances that are restricted in cosmetics. And we also screen out substances that are listed in the Annex 3 inventory of REACH, also based on the classification and labeling notification that has been received by ECHA for those substances. And we ended up with 5 or 6 alternatives, potential alternatives per case studies after this property study. Then concerning the technical and economical feasibility, for us as academia, it's really difficult to perform this because it depends a lot on the product and on the company who is using the substance. But concerning the technical feasibility, during the interview with industry, they told us that around 25% of cosmetic products are reformulated every year. So it seems that in the cosmetic industry, it's quite easy for industry to reformulate the product. So we considered that if the alternative has the same technical function as the case study chemical, then it is technically feasible to substitute. For economical feasibility, unfortunately, we couldn't assess it at all because we're not industry, so for us, that's impossible to do this. Then for the hazard assessment section, we based our work on this guidance from the OECD that listed key considerations to identify and select safer alternative. So we consider hazard endpoints not only mobility, but also persistency potential, bioaccumulation potential, enterprise perception, and all the human and environmental toxicity that are listed in GHS. In total, we ended up with 26 endpoints, hazard endpoints, for antigen assessment. Here are the source of the data that we use. So we use both experimental and QSAR data. In this figure, everything that is blue is coming from experimental studies. Everything that is brownish is coming from QSAR data. Everything that is gray is data gaps. So you can see that there are data gaps everywhere. So we need to come up with a method to handle the data gaps. And we need to come up with a method to actually compare, because we have like 26 hazard endpoints. How do you weight each hazard endpoint together? So that's what we try to do afterwards when we try to compare the alternative. So for that, we used 3 different multi-criteria decision analysis methods that have been used by previous studies. So we used the heat map, the MOLT method, and the collector-free method. And here in this table, you can see the final ranking that we got for each of these 3 methods. And we considered that an alternative was safer than the chemical of concern if it was ranked better in all 3 methods. So what you can see here, they are like added in the green, is that we could find safer alternative in each case studies. And you can also see with the one highlighted in the red, that there are also candidates that are worse, or that we expect them to be worse than the chemical of concern. So there is a risk of regrettable substitution from happening here as well. But we did find a safer alternative for each of our case studies. So then, are there no safer alternative available? The answer was no. So then we stopped our assessment here, and we didn't try to evaluate whether the use of those chemicals were necessary for health and safety, because there were alternatives available. So then we could conclude that those uses were non-essential. To summarize, this study proved that the essentiality of use mostly depends on the viability of safer alternative. So even if we start implementing the essential use concept in regulation, etc., there is still a strong need to have proper chemical alternative assessment in order to avoid regrettable substitution from happening. And the functional substitution approach that has been proposed in 2015 is a really good tool to identify uses for which such a detailed chemical alternative assessment is not needed. Looking forward, in this work we didn't evaluate the reliability of the hazard data, and this is highly important if you want to have more confidence that the alternative is indeed safer. Also, we didn't assess the technical feasibility and economical feasibility because we couldn't, but further we should implement this into the multi-criteria decision analysis if we want to take everything into account. And also, we focused here on the use case of chemical and we didn't have the life cycle perspective. Again, if you want to be sure that alternatives are safer and want to avoid regrettable substitution, we should implement such life cycle thinking into the assessment as well. And with that, I would like to thank Johanke, who collaborated with me on this project, Gerard Brenner from Cosmetic Pre-Op, and Eloise Todelier from Egypt Minerals, who talked with us. We're great to have the interview with us to provide the industry perspective, and 0PM and the EFRS 2050 projects for the funders.
0PM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.